Well, we're about done with our discussion of astronomy, and I had a little bit of extra time to put into the videos for this week, and I thought, since what I do in my professional life is I study string theory, and since the question of how quantum gravity fits into the framework of cosmology has come up at several points during this class, I thought I would give you a very brief and sort of idiosyncratic introduction to what we mean by string theory for those of you who are interested. So let's recall what the problem is that string theory tries to address. We have an issue. As a theoretical level, the issue is that general relativity is an incomplete theory. It cannot possibly be the full theory of gravitation. The reason is that there are singularities in which general relativity is indeterminate. And yet we have theorems by Penrose and Hawking that we discussed that say that if you take most initial conditions for general relativity and try to predict the future or post-dict the past, within a finite time you develop a singularity, and at a singularity the equations break down. You get infinite curvatures. What does a singularity mean? Well, a very good example of a singularity is this cone. This cone can be obtained by taking a piece of paper. I have my demonstration piece of paper, and on a good day I can fold this to produce a cone if I'm not thinking about it. What this shows us, again, because I can make a cone out of this, I think, without tearing the paper or stretching it, a cone is actually a flat space. It has zero curvature, so relativity on a cone should be pretty straightforward. In fact, if you draw straight lines on the paper and then fold it, those will be the geodesics, the straight lines on the cone. And here we've drawn a couple of geodesics, interesting geodesics on a cone. And so particle propagation on a cone is very trivial. Particles will propagate along these geodesics. This is all nice until it crosses somebody's crazy, sick mind to send a particle on a trajectory that was supposed to be a geodesic that hits the tip of the cone. At the tip of the cone there is curvature. There is infinite curvature, in fact, because there's a sharp tip. And theories of particle propagation on a cone don't tell you what happens when the particle gets to the tip. The equations are indeterminate. There is a singularity. General relativity produces such singularities and then cannot predict what happens. This is an example of this is the Big Bang, an example that interests us. Finite time in the past, absent some inflationary scenario, there was a singularity at which densities and curvatures were large. The end of a black hole, of which we spoke so much on the forums, a black hole that evaporates by Hawking radiation, at the end is a very small black hole, and there's a singularity there. The fate of matter falling into a black hole, all of these are issues where general relativity is incomplete. Now, one of the reasons we think that this would be ameliorated, what we think tamed. So if this were a real cone, say if I produced this cone out of some metal and I managed to sort of eliminate scattering off the ions and I had ballistic electrons flying through this metal, then I know what would happen. If I sent an electron to the tip, then it would depend what the metal shop did with the tip. If you magnified the tip, you'd see that it has all kinds of lumps, and the electron would travel on a geodesic through the lumps. The fact that there's a singularity here, a real physical piece of aluminum would not be singular. A real physical piece of aluminum, when you magnify it, is smooth. And the reason it looks singular is because you're omitting some details that are usually not important. Maybe there's a little wiggle here, but it's not crucial. Here, the wiggles are crucial. What you've done to get a singularity, an infinity, is you've found a divergence because you neglected something that has become important. What are we neglecting? Well, at large values of the curvatures, under exactly these circumstances where general relativity is singular, quantum effects are expected to become important. The problem is that applying the traditional methods of quantizing renormalizable quantum field theories to the general theory of relativity leads to a failure. It leads to conceptual failures. It leads to technical failures. The theory is not renormalizable. So if you do a perturbation theory, you find that renormalizability fails. It is also conceptually very complicated. To treat the interesting problems in relativity in a quantum mechanical way is very complicated. So general relativity cannot be the entire story. Quantum effects are important. Note they're important under somewhat strange circumstances and for the purposes of doing most kinds of physics, quantum gravity is completely irrelevant. Why dedicate your life to this? Well, because physics is supposed to be the science of universal laws. We've thrived throughout this class on the statement that the same laws that apply on Earth apply in the Crab Nebula. The same laws that apply on very small distance scales, the scales of the Planck scale at which quantum gravitational effects should be important, should apply at large distance scales. We should have a unified physical law that describes the motions of planets as well as the gravitational fluctuations at the Planck scale, and we do not. So we are not done with the program of physics. And what is string theory? Well, string theory is an attempt to resolve the situation. What's a crude way of describing string theory? String theory is what you get if you imagine that instead of particles, so what's a particle? An electron, a quark, whatever it is, a particle is an excitation of the universe that lives at a specific point in space and time, in space at any given time. So its history is given classically by its world line, its trajectory in space-time, and then there's a quantum mechanical version of that same description that replaces the trajectory by wave function, and in a relativistic theory by excitations of a field. We know how to do all of that, but the starting point, classically, is a particle lives at a point in space. Now, imagine that instead of a particle which lives at a point in space, you replaced everything with a string. So this is a particle. What can a particle do? A particle can move. You put a particle in a box and watch my wonderful animation make it move. What can a string do? Well, a loop of string, for example, this is what's called a closed string, can also move around in a box, and it can emulate a particle well. But a loop of string that is not going anywhere, if you run and catch up to a string and sit in its rest frame, a particle in its rest frame is just a particle. It's sitting there. Maybe it has a spin up or spin down degree of freedom. A string in its rest frame can wiggle and vibrate and spin and twist and do an infinite, essentially, number of things that a particle can't. Now, when I say a string, what is a string? In the sense that a particle is an excitation with some energy that lives at a particular point in space, a string is an excitation that lives in a particular one-dimensional piece of space. A string has no thickness. It has no substrings of which it is made. No more than an electron has subelectrons out of which it is made. It just is. And the dynamical variables of a string is where the string, which part of space the string occupies at any given time. And even if the string is not moving, that part of space can be, not globally translating, that part of space has an infinite number of motions it can do. Essentially, there are harmonics, there are waves that run around the strings can vibrate. This makes a theory of strings infinitely more complicated than a theory of particles, because a string can do an infinite number of things. Now, but it's also infinitely more interesting. Why? Well, one idea is that a string, the energy of a string, well, a string has a tension, just like the string between quarks. It's a constant tension. Its length determines its rest energy. But a string is never at rest. It's always wiggling. And there's energy in its vibrational motion. And so a given string, by being excited to different degrees in different modes of its vibrational motion, can describe all manner of particles with all kinds of energies when in their rest, with all kinds of masses, because the wiggling energy of a string is the energy of the string in its rest frame where it's not going anywhere. Well, that's what's called mass. A string can also realize angular momentum very readily. A little loop of string can be actually mechanically spinning. So you can have a very natural way in which particles have angular momentum as well as energy and mass. All manner of different masses and different angular momenta can be expressed by one universal string. Okay, so you have one unique kind of string, and it corresponds essentially to an infinite kind, one for each vibration mode, vibrational state of the string. An infinite number of particles represent different kinds of particles represented by one string. What's so great about this? Well, we only have a finite number of particles, we think, in the universe. Who needs an infinite set of particles? Well, string interactions is another interesting thing. So, what is the story? So this is the sort of history that goes with one of those Feynman diagrams we drew. Here, an electron is scattering off a positron by first merging to form a photon. Note that conserves charge, and then the photon decays to an electron-positron pair. And how does this look in a string picture? Well, remember, we replace each of these particles by a little loop of string whose vibrational state tells it that it's an electron or a positron or a photon or whatever. And so we have two little loops of strings in two different vibrational states, And the strings in a theory can be open strings with two ends on the edge, or they can be closed strings. We're going to focus on closed strings. So the way that strings interact is a unique idea. There's only one interaction if two strings at any point along their world line one point occupies the same event, the same point at the same time. In space-time, they can split and join. In other words, two strings coming in this way will most of the time go through each other, but with some probability, the four edges coming into such an intersection the four edges coming into such an intersection will trade roles. So as a string wiggles, for example, if one point in a string wiggles so it's close to a figure eight, it can pinch off and break into two strings. And so the string version of the interaction we saw before of an electron and a positron merging to form a photon, and then the photon splitting to form an electron-positron pair would be described as two strings in some vibrational state corresponding to whatever particles, merging, and then the oscillation of the merged string causing it to split again into two particles. This is very nice. What's the point? What does it buy us? I mean, it's certainly very complicated. Now, electrons look a lot like particles. We've been studying electrons. We have no reason to imagine that an electron occupies more than one point in space. How do you reconcile this with the idea that an electron is a loop of string? We certainly don't see an electron occupying a one-dimensional space. Well, the idea is, of course, these strings are very tiny. Their distances their lengths are typically of order the Planck length, very small, 10 to the minus 33 centimeters, much smaller than the smallest resolution of all our experiments at all our accelerators. So if you look at a string from a great distance, it looks just like a particle. It looks like it occupies a point just because you're not resolving the size of the string. So if you can't see them, and by see I mean even if our accelerators can't resolve them, what's the point? Who cares? So everything's a string, everything's a schming. It looks like a particle. I have a good theory of particle physics. Why discuss string theory? Well, the idea is, there are several ideas. One is that string theory is naturally what, in fancy words, is called the theory of everything. When we describe the standard model of particle physics, we write a theory that has up quarks and down quarks and strange quarks and top quarks and bottom quarks and charm quarks and so on. And they have the masses or the couplings to the Higgs field that we measured them to have. We could write equally well another theory which had a completely different spectrum of particles with different charges, with different interactions, with different masses, and that would be just as good a theory, just wouldn't describe our universe. In string theory, I never said anything about what kinds of string I have. I just said I have a string. And it turns out that there's only one universal kind of string, and all the observed particles in nature are posited to come from the same string, and the properties of the particles, as I said, are encoded in their vibrational state. So once I said string theory, I've said something definite. One of the vibrational states of a string is this one that I represented before, where the vibration is sort of a quadrupole thing. The string elongates in one direct dimension and then in the other dimension. And you can study what kind of a particle would a string like this describe, would a string that does this as its oscillation mode. And you study it, and when string theory was first proposed in the 70s as a theory of the strong interactions, essentially trying to describe what we now know are the flux strings between quarks, this is the reason people stopped, or most people stopped studying string theory in the 70s, because the particle that this describes turns out to be massless, have mass 0, and spin 2. And everybody knew there was no massless spin 2 particle, or very light spin 2 meson in the spectrum of... and so they ignored this theory, other than a few crazies who realized we know about a massless spin 2 particle. The graviton that carries gravitational interactions would be a massless spin 2 particle, and in fact you can prove that any massless spin 2 particle and any consistent theory it couples to matter through the couplings that a gravitational interaction would have, as determined by Einstein's theory. So if we have a consistent theory of anything here, we have a consistent theory of gravity. That's great. So maybe strings will, per force, include gravity. This often is cited by jocular string theorists as saying, here's the only experimental prediction of string theory. String theory predicts that when I drop this pen, it will fall. Why? Because unlike other theories where you include the existence of gravity because you've measured it to exist, once you say strings, every string theory contains gravitons. Great. So string theory predicts gravity. That's not why we study it. The point is that string theory in a quantum mechanical sense is better behaved than particle theories. If you watched my clip on quantum field theory, then I said that in quantum field theory, the interactions take place at these vertices, and when you draw diagrams that lead to divergences, to problems with calculating with infinite answers to calculations, something which in renormalizable field theories is just a property of asking a silly question. In gravity, it happens even with the answers to physics questions. This came from regions, from situations where these vertices were all on top of each other at the same space-time point. Now remember that the string analog of such a vertex is what is called a pair of pants. It's basically, imagine time flowing to the right. These are two strings, and they're merging to form one string, and their merger occurs right about here. But the way that two strings merge and the way that two lines merge is very different. There is a particular event, a particular point where all three lines touch. If you try to indicate the exact point here where the two strings merge, well, if you slice it, you can see there's two strings at this time and there's at this slice, and there's one string to the right of this point. Well, yes, very nice, but if you remember that I can draw this with the bottom sort of rounded off. Imagine this is a U-shape a pair of pants, then if I look at it slightly differently, I see two strings here and two strings here, and this would be the place where they join. There is no unique point that is the place where the two legs of a pair of pants join. You can make it completely smooth, and there's no singularity, so there's no issue with these points coming ever closer. This is a graphical manifestation of the fact that indeed when you do the same kind of calculations with strings that lead to the meaningless divergent results in an attempt to quantize gravity as a particle theory, you don't get the same kind of divergences. So if string theory is a theory of gravity, then it has a good chance to be a consistent quantum theory of gravity. It does not in the particular run into the same problems that other attempts to quantize gravity have run into so far. Okay, so maybe we have a consistent quantum theory of gravity, but it's very difficult to do anything with it because you have this infinite degrees of freedom of a string. This is what makes the theory complex and why we don't know a solution to string theory. We don't know the space of solutions. We don't fundamentally understand what string theory is. What I'm describing is sort of one approach to it. There are several, and this captures some of the properties of string theory, this idea of thinking as strings, but we know it is intrinsically not a complete description of the theory. There is not a dynamical principle. It is not as solid as our understanding of, say, quantum field theory. We're still working on it. Why is it worth doing? Well, here's a good example. So, if you are looking at a space that is large and curvatures are small, then if you look from far away, we said a string looks just like a particle. But near a singularity, some things get very small. And near a singularity, it turns out strings behave in very different ways than particles. In what sense? Well, here's a little, I'll draw it in red. Here is a little loop of string. And I could take a little loop of string here and ship it up that geodesic, and whatever vibrational state it has will just fly around that geodesic just like a particle would, and I can send a blue string up this geodesic and a green string up that geodesic, and everything would be hunky-dory. But you can ask, what happens if I take this string, and instead of shooting it along this geodesic, I aim it right at the singularity? Well, that depends on the nature of the singularity. But if the singularity is a particular kind of conical singularity, kind of like the one I drew here, then we have a way of understanding it, and string theory teaches us that here is how strings differ from particles. In addition, so if we're doing a theory of closed strings, I can have loops of string that look like this, but I can also have a loop of string that looks like this, that wraps around the top of this cone, that lives in the cone by wrapping across the edge. Now, this loop of string will never get very far from the edge because remember, it takes energy to stretch a string, and as the farther it gets from the edge, the bigger it would have to get. So it would take a lot of energy to move this guy down. So this describes something like a state of the string that only lives near the tip. Okay, so strings have extra degrees of freedom that live near the tip of a conical singularity. So what? Well, the behavior of the bits of string far from the tip is very much like particles. because if you don't look too closely, a string looks like a particle. But when they come up to the tip, these strings interact with those strings, and taking that into account leads to reasonable dynamics. In other words, if you throw this string at the tip, you can actually predict in a reasonable, finite, divergence-free, singularity-free way how it will propagate through the tip and beyond. So some kinds of singular spaces, and this cone is an excellent example, lead to completely reasonable and non-divergent and non-ambiguous string dynamics. So maybe the issue, that the promise that suggested that string theory would be a quantum theory of gravity and therefore would correctly tell us how to discuss the singularities with which general relativity is plagued, well, this is a first and somewhat encouraging sign. I should say that only some singular spaces lead to reasonable string dynamics. There are spaces on which the string dynamics can be singular. Okay, so string theory is worth it. It comes with a price. One of the properties of string theory is that when you study the relevant kind of string theories, they suggest that at least at the scale as seen by the string, space-time should be 10-dimensional, or a space should be a 9-dimensional space. We, of course, live in a 3-dimensional space, or a 4-dimensional space-time, so that's a little bit of an experimentally verifiable prediction that is false. What do we do about this? Well, early approaches to this problem, to trying to reconcile the fantasy of string theory with perhaps something realistic, involved the process called compactification. The idea is, well, this is a theory of gravity. This describes, among other things, the shape of space, the curvature of space. We can imagine that the extra dimensions occupy a small volume and they're too small to measure. What does that mean? Well, again, I'm going to work with two-dimensional things because that's the most I can draw. Imagine a two-dimensional object that is the surface of this donut. Remember, we said a donut is flat, but this one in 3 dimensions is not. And so when I say the two-dimensional surface, there's no inside or outside to this donut. We have a two-dimensional bug made of ink, say, that can crawl up and down this donut or around this side. And this bug lives in a universe that is perhaps flat, but certainly finite in 2 dimensions. He lives in a 2-dimensional universe. Now imagine that I shrink one of these circles till the radius, the distance, the circumference of the circle, the smaller circle in this donut, is so small that it's a distance of, 10 to the minus 33 centimeter, much too small for the bug's most powerful accelerator to detect a displacement in that direction. This means that the bug will still be able to detect things moving up and down. This can be light years, and this can be very small, but the bug will never detect that there's another direction in which things move. In the very real quantum sense, he will occupy equally all positions around this circle because he's a big fat bug, like I'm a big fat person. And if you have a direction in which once you move 10 to the minus 33 centimeters, you come back, then my wave function is smeared equally over all parts of that circle. And so this bug would then interpret what he measures as being a one-dimensional universe unless he developed a really powerful accelerator that could see 10 to the whatever centimeters the distances are along this small circle, and then he would resolve that actually the dimension of his space was 2. In a similar way, we imagine that our space is actually a 10-dimensional space, but 6 of the dimensions are a very small space. So what this means is when the bug states, I am here at this point in my one-dimensional universe, what he's really specifying is which circle of the 2-dimensional universe he's on. So if he thinks he's here, he's somewhere here, or overall, everywhere on that circle, is what I was saying. And so his one-dimensional universe is really a collection of circles. Imagine that our 3-dimensional space really is a collection of 6-dimensional spaces. So at every point in our 3-dimensional universe, install a very small 6-dimensional space. And imagine that when I say I am right here, I am really also everywhere along this very tiny extra 6-dimensional space that we can't move in. Okay, well, great. It turns out that the shapes of these internal spaces, as they are called, are constrained by something like the equations of motion of the string. We look for solutions of the string equations of motion. It turns out that only a particular kind of 6-dimensional shape will do, something called a Calabi-Yau space. Very exciting mathematical object. This is some representation of an object that is actually a four-dimensional space, so it's a lower dimensional Calabi-Yau space. Of course, the colors here represent some of the dimensions, because this is drawing a surface trying to represent a four-dimensional object. Good, so this compactification is a way to reconcile the silliness of 10 dimensions with the reality of 4. Why am I bringing it up, other than because I like to study the geometry of spaces and the string theories on them? Well, because there's an interesting property that one discovers when one studies precisely the kind of universe that this bug was living on. So let's imagine what we call a garden hose universe. It has one direction that is non-compact, and so that is infinite. So a bug can move to the left and to the right along this thing forever, but the other direction, so this is a two-dimensional example because I can draw it, in the other direction the world is finite, so it's periodic. You go and you come back to where you were. Well, again, in this situation, strings differ qualitatively from particles as soon as the radius of this small direction becomes small compared to strings, because you can have strings like this one. Well, this is about the same as a particle stuck in the middle. It has some oscillation, so it carries some energy. But there's something a string can do that a particle cannot, and that is this string can be wound all around the universe. Remember, this is a closed string. You can't break it. The universe goes on forever. It has no inside. It's a two-dimensional universe. You can't unwind this. This string carries what, if you want, a conserved quantum number. The fact that it winds. These strings have directions on them. So if you have another string that is wound in the opposite direction, then these two can annihilate. We really have a conserved quantum number called winding number, and this is a string of winding number 2 that somebody tried to draw here. Right? So this is a string that winds twice. This has double the charge. Now notice that if this tube is very large, if the periodic direction is large, it takes a lot of energy. These winding strings are very massive states, but if the tube becomes small, they become light. Now, these strings that are not winding can, of course, be moving around. You can take this guy and kick him, so he's going at some frequency around the universe. It turns out that that frequency is quantized, and in a universe where the distance around the circumference is small, the lowest energy of the lowest non-trivial motion around this becomes high. So as you squeeze the garden hose down, the winding strings become light and the moving strings become heavy. If the hose becomes large, these become light and these become very massive. What it turns out is that in precisely a situation like this, where we have a circle in the universe, there is a duality called T-duality that says that those two situations are describing the identical string theory. It's just a change of variables. It depends what you call which. If you relabel what you call the winding string and pretend it is a momentum string, a motion string, and what you call the motion string with 2 units of minimum motion in this direction to be a string with 2 units of winding, not only the spectrum but the interactions and the entirety of the string theory of theory where the circumference of this thing is 2 pi r is given by some radius. Or if you replace that r by 1 over r, note you can worry about dimensions. This has dimensions of length. This has dimensions of inverse length. Indeed, there is in string theory a parameter with dimensions of length squared, which is roughly the string tension, energy per unit length of the string. That turns out, after you put in all the c's, to be the same as dimensions of length squared. This duality tells you that a small circle and a big circle, if you make r very small compared to the string scale, or very big compared to the string scale, you get the same theory. In some sense, in string theory, the size of space is indeterminate. If you try to generate a problem for string theory by squeezing the space very tightly, string theory allows you an alternate discussion in which it's completely smooth and flabby and large. That string theory has some sort of, and of course the smallest relevant radius is radius 1. Why is it that string theory has a natural radius? Well, it has this dimensionful parameter with units of area, and the square root of that is a length, and basically that's like a minimum distance. This is roughly the average length of a string, and in some sense asking where a string is to better precision than its average size is a silly question. A string is fuzzy. It's scattered around and it wiggles. And so when you try to ask generate singularities and putting 2 strings on top of each other, they're soft, they're flabby. This is why the ultraviolet behavior of string theory is in some sense better than that of quantum field theory, and quantum gravity makes sense in string theory. Now, there's an extension of this kind of T-duality to the more general, not just circle thingy, Calabi-Yau shapes. It's called mirror symmetry, and this turns out to relate to Calabi-Yau spaces that are topologically. These are distinct in the sense that you can't switch one into the other by stretching and pulling. You'd have to break it. These are as different as spaces can be, and yet string theory on one of them is identical after you relabel things to string theory on the other one. So not only is the size of space indeterminate, if you're living in a universe that's described by string, someone asks you how big, the universe is periodic, how big is it? Well, there's two answers, we said, that can't be distinguished by a string theory. Moreover, if someone asks you remember we talked about the topology of our space, and we said we don't know the answer, but it might have an answer. In a string theory, at some level, the topology of space is undetermined. There are two different topologies that lead to isomorphic identical physics. So this is another interesting way that strings differ from particle theories. Why am I telling you all this? Well, this actually because I like it, this because it gives us another sense for this ultraviolet softness in the way that string theory ameliorates singularities. Another interesting property, I told you that strings were not the end of the road. The description in terms of strings is partial at best. Just as general relativity predicts black holes, string theory predicts black objects. Now, string theory lives in 10 dimensions. There's room for lots of different black things. It turns out that you can find in this 9-dimensional space black objects of dimension 0, that's like a black hole, or dimension 1, that's like a string, or dimension 2, that's like a membrane, or dimension 3, all the way up to 9-dimensional objects that fill all of space. Now, these are objects that are, in some sense, made out of strings in the same way that a black hole is made out of gravitons. So, or that an electric field is made up of many, many, many photons, a constant electric field. These are the constant modes of the... these are some configurations of the field of strings, but we don't really have a good formulation for what the field of strings mean. But like every configuration, there can be excitations around it. So you can have a brain or one of these black objects that fills, say, some surface in space, but then that's a configuration with some energy. It takes energy to create this thing. There's a configuration with a tiny bit more energy once you have it, where it wiggles a little bit. In a relativistic theory, if something exists, it can also wiggle. And so you can study the wiggles, the excitations of this, ripples flowing up and down this brain. And in general, in theories of physics, there are always such black or solitons, they're called, such complex field configurations, and they have excitations. And studying their excitations is very complicated. In string theory, a miracle happens. All of these excitations can be described by strings. What do I mean by strings? Well, you add to your theory, which had closed strings in it, open strings with the restriction that the edges of the open string must lie on the brain. The tips of the open string lie on the brain. Remember, strings don't like to be long, so these are, again, excitations that only live in the space occupied by the brain, as you would expect for something that describes wiggles of the brain. And then those open strings interact with each other and with closed strings that propagate through the rest of space by the usual splitting and joining interaction. There's just one interaction and one parameter in this whole entire theory. And so these D-branes have their interactions, and this process here, this sort of world tube, describes a closed string that bounces off the brain, or if you want, you can think of it as interacting with this open string on the brain, and you can compute such properties. And the realization that the excitations of some of these branes were described by open strings allowed us to make calculations of their properties. And in particular, when you have a particular kind of singularity, then you can have strings that would create virtual branes. Branes typically are very massive objects. You don't create virtual black holes. But we do if you manage to make the black holes, or the branes in this case, very light. How do you make a brane very light? Well, a brane, again, if it's a two-dimensional object, has a given very large energy per unit area. Now, what you can do in a sort of tube universe like we had before, if you have one-dimensional branes, then the one-dimensional branes, just like strings, well, they're called D-strings, they're kind of like strings, they too can wrap the one-dimensional universe, and if this one-dimensional universe becomes very small, then although they have a high tension, the mass, the energy it takes to wrap a brane there is not very large. In the context of geometry, what you can do is you can take these branes and wrap them around such circles or holes in your Calabi-Yau space of varying dimensions. And then it turns out that one way to take a smooth Calabi-Yau space and sort of squeeze it until it becomes singular is to imagine that you take some of these holes and you squeeze them until they have zero area. And when the hole has zero area, this indicates a singularity. Those kinds of singularities, when that happens, then you can imagine that a string coming towards the singularity can actually create or interact with a brane that wraps this zero-size hole, so this brane is very light. And incorporating those very light branes, wrapping those very small holes in the singular space, allows you to understand more kinds of singularities than we understood with just the winding strings that wound around conical singularities. And this is very important because let me imagine that the universe everywhere is described by some Calabi-Yau space. And then I tweak this Calabi-Yau space, and so I send a gravitational wave propagating through space where the Calabi-Yaus wiggle, they change a little bit. And I can adjust my wave so that I start with the Calabi-Yau space, and as it goes on, the Calabi-Yaus change in such a way that at some point the Calabi-Yau becomes singular. And I can ask what happens after that. And what this allows me to do is to describe that gravitational wave in a smooth way in string theory, although in general relativity you start with that solution of Einstein's equations and you perturb it and you get to a singularity and Einstein's equations break down. There's infinite curvature there. And so, again, this is a situation where correctly thinking about string theory, though when string theory was formulated, certainly nobody knew about D-branes, correctly thinking about it allows us to treat situations in which general relativity fails. Yet another indication that string theory is an interesting theory to study. I should point out that once we deal with compactification of string theory, the beautiful uniqueness that said there is only one string theory, there are no free parameters, is kind of lost because there are many topologically distinct Calabi-Yau spaces, and only some of them are mere pairs. So there's still a large number of them. And many of them have parameters. They come in families. You can sort of take this Calabi-Yau and then you can change it a little bit and get another Calabi-Yau. So there are continuous parameters. There are continuous families of Calabi-Yau. So now each of them describes some four-dimensional theory. And depending which geometry you pick for the 6 dimensions, you get a different physical world in 4 dimensions. The effective theory in 4 dimensions looks very different. And so now the unique string theory is replaced by each Calabi-Yau can be thought of as one solution to the string equations of motion, and we have lots of solutions to the equations of motion, and now there are lots of, it's as if you had lots of theories, you just have to figure out, if you're optimistic, which of them describes the real universe. We are very far from knowing anything like enough about string theory to make such a calculation, but I'll discuss a different approach that string theory suggests in a moment. Before that, I want to think of another application to D-branes, as you can get rid of compactification. Perhaps the reason we perceive that we live in a 3-dimensional world is that our 3-dimensional universe is a 3-dimensional brane, an excitation, inside some 9-dimensional, 10-dimensional, if you include time, string theory, but we are made of open strings. What do I mean we? I mean electrons and quarks and gluons and photons, and everybody's made of open strings. You can invent theories where the excitations of the brane look very much like our universe, all kinds of gauge theories and the kind of quantum field theories that describe our theory, our nature as we know it, would arise if you didn't look too closely, if you didn't have a resolution of 10 to the minus 33 centimeters on one of these branes. And then, of course, we can't leave in the other directions, not because they're small and we essentially occupy all of them, but because the stuff we are made of is confined to the world volume of a brane. So our space might just be a slice in a universe of higher dimensions. And, of course, closed strings can move off the brane. They are not tied to the brane. And, for example, our wiggling friend, the graviton, does lead to gravitational interactions between matter on the brane and matter off the brain in what this cartoon whimsically calls the dark. Now we have these continuous families of string theories. What that means is the parameters that specify the members of the family are the values of massless scalar fields in the theory. Oh, we like scalar fields if you want to do chaotic inflation. We remember that the values of the scalar fields is what acted as the inflaton. In fact, massless scalar fields are a problem because we don't detect any light scalar fields other than perhaps the Higgs in our universe. But you can imagine some modifications and corrections that would reduce this continuous families of solutions to discrete solutions, but many, many, many different, large numbers of them, so that you would have sort of a solution, and then there would be some theories that are not a solution. If you tried to continuously change the parameter, you'd be increasing the energy, so it's no longer a solution to string theory. Then there would be another solution over here, and roughly a many-dimensional analog of this wiggly space would be the energy surface of the string theory as a function of, here, 2 parameters, but you can imagine hundreds of them. And each valley here is actually a string vacuum, a solution to the equations of motion. The theory can just sit at the bottom of them. And we can imagine transitions either through tunneling or through quantum fluctuations between these, and notice that these valleys can all have different heights. The height of the potential corresponds to the cosmological constant. So you can readily discuss this landscape, many, 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 many models with many values of the physical parameters and many values among them of the cosmological constant. And it is possible to construct, with some effort, models like this, which seem to have parametrically tiny non-zero cosmological constants, which makes them viable models for sort of the universe we live in. They're not unique. There are other models with larger cosmological constants, but that's okay. Remember, in the context of chaotic inflation, we happen to live in a piece, one baby universe that, when it branched off, has a very small cosmological constant, that elsewhere there are universes with big cosmological constant. Just means we don't live there. We couldn't. Those universes never make stars. So, in fact, this string landscape, this existence of large numbers of potential exact string solutions, is one of the reasons that has led people to consider taking seriously this picture of the multiverse and trying to understand, by studying its properties, what we can expect the properties of our universe to be. This is a very speculative theoretical investigation at this point. So I haven't really told you much about string theory, but I told you something. And it's still in no sense a physical theory. I hope I emphasize this. But already, before, and this is the point I wanted to take, before we have a real theory, we've had lots of new ideas about space-time. We have these ideas about winding theories and strings that give us this idea of duality. We have an idea of this mirror symmetry that relates spaces with different topology. We have, it turns out, non-abelian versions, these winding strings lead to a discussion of a space that extends, sort of, when the strings are pulled far apart, looks just like space, but when they come close, looks like a more complicated object. So you get space effectively emerging from something more complicated. And there's reason to believe that in general this is what's going to happen in a consistent quantum theory of gravity, and indeed in string theory, that the very concept of space-time, we're not going to start the discussion as I did today by here's a space and here's a string propagating through it. But I'm going to say here's a string, and I will study its properties, and one of its properties will turn out, under suitable conditions, to look somewhat like the position of an object in space. And then in 4 dimensions, I say, aha, this string is a 4-dimensional, describing a 4-dimensional universe. So space and time, or at least space, time is more confusing often, are expected to show up as an emergent feature, not something you put into this theory, but something that comes out of the dynamics without being specified a priori. And this presumably will lead to deep new insights about the meaning of space and time, and in particular, how to treat questions like the evaporation of a black hole or the Big Bang, I should say in advance that while string theory has given us many new ways to think about both of these types of problems, it has not actually completely resolved any problem, and in particular, it is not yet a theory. So there is a lot to understand, and there's a lot to keep people like me busy, and if you want to join us, a lot to keep you busy too.